Hello, everyone. In this video, we explore some consequences of the existence of the matrix P, which is a product of elementary matrices we discussed last time. Here's the setup in which we'll frame today's video. We have an M by N matrix A, whose reduced row echelon form is a matrix R. And as we saw in the last video, there's an invertible matrix P such that PA is equal to R. The first consequence of the existence of the matrix P is the following. If we consider an augmented matrix AB, and we suppose that its reduced row echelon form is the matrix R and some other vector C, then what we know is that the linear systems AX equals B and RX equals C have the same solutions. Why is this true? Well, we saw that, if R is the row reduced echelon form of A, then there's row operations in here, R1, R2, R3, and so on, that lead us from A to R. Now, doing the same row operation to the augmented matrix, R1, R2, and so on up to Rk, will give the same matrix R when we work with the part of the augmented matrix corresponding to A and some other vector C. That's the C that we're working with in this first consequence. A consequence of this is that R is obtained by multiplying A by P, but the same matrix P encodes the same row operations, so also C will be given by P times P. Now, suppose that we have a solution to the linear system AX equals B. Call the solution V. Then we know that A times V is equal to B. If this is true, then we can multiply both sides by P and get P times AV is equal to PB. But what we just said, PA is equal to R, so we get that RV is equal to PB, which is equal to the vector C. In other words, V is a solution for the linear system Rx equals C. What this shows is that the set containing all solutions to AX equals B is actually a subset of the set of solutions of Rx equals C, because every solution of AX equals B is a solution of Rx equals C. We can also prove the converse. If we have a solution to Rx equals C, let's call it U, I can apply P inverse to both sides of this equation, and I get P inverse of R, U, is equal to P inverse of C. But let's remember what R and C are. The matrix R is nothing but P times A, and the vector C is nothing but P times B. When I have P inverse times P, those become the identity. So the final result from here is that AU is indeed equal to B. What we showed at this stage is that the solution to the set of solutions to Rx equals C is contained in the set of solutions to AX equals B. We showed that both sets contain one another, so we can finally conclude that they're the same set. This is the first consequence of the existence of an invertible matrix. The second consequence is maybe the most important enough to get its own name, which is column correspondence property. Let's try to think about what it entails. Suppose you have a matrix A. It's given here. It's a 4x6 matrix. The first question that I could ask you is, are the columns of A linearly dependent? And the answer would be yes, because the columns of A are vectors in R4, And so there can be no more than 4 linearly independent columns. So if I look at all of them, they must be linearly dependent. So yes, for dimension reasons. Because we have 6 vectors of R4. This answer is not too bad, but if I start asking you, what are the relation between these columns? We know relations exist because the columns are linearly dependent. It becomes a little bit harder to understand what the linear dependency relations are between these columns. And this second consequence is an answer exactly to this second question. The first thing to do towards an answer is to compute the row reduced echelon form of A. It's computed here. And I just highlighted the pivot columns. There's those 3. And then the non-pivot columns are the 3rd, 4th, and 5th, and 6th. So we can answer question 2 for R. Here's a little bit of an answer. What we know for sure is that the pivot columns are linearly independent from one another. So if I take a set containing the pivot columns are standard vectors, different standard vectors, so they're linearly independent. And once we have the pivot columns, it's not too bad to write relations for the other columns. Let's take, for example, the second column, R2. Well, that column is twice the first. If I were to write R5, which is this column over here, to do that, I would have to use the R4, which is E3, minus R1. So I can write it, maybe I'll keep the order. So I'll write minus R1 plus R4. I can write it as a linear combination of 2 of the pivot columns. Let's have a look at the last one. This should be minus 5 R1 minus 3 R2 plus R3. Let's go back and check that I copied everything down. This is minus 5 R1 minus 3 R3 and 2 R4. So there's something slightly off. Minus 3 R3 plus 2 R4. So we have linearly independent columns and relation between the linearly dependent ones. What the column correspondence property tells us is that the same relations hold for matrix A. Let's have a look at it. Well, first of all, the column correspondence property tells us that the columns A1, A3, and A4 in A are linearly independent. Remember, so these are the columns that correspond to columns R1, R3, and R4 in R. The reason why this is true, well, we can check it immediately, is that if I cooked up a matrix that only had these 3 columns, A4, those are the 3 columns coming from matrix A over here, 1, 2, and 3. Then the same row operation would give me a reduced row echelon form that leads to the same 3 pivot columns in R. And that implies that the set that I started with was linearly independent because there's as many pivots as there are columns in here. But something that is even more astonishing is that these relations here will survive. So we saw that R2 is twice R1 and R5 is minus R1 plus R4. The same thing can be said about columns of A. This was minus 5A1 minus 3A3 plus 2A4. This is magical because it gives us relations on columns of A without even necessarily knowing what A is, as long as we know its row-reduced echelon form. Let me just comment on why this should be true and why is it a consequence of the existence of P. Let's see. So if our matrix P exists as we've been using it, PA is equal to R. But if we expand what PA means, PA is just P multiplied by each column of the matrix A. In other words, writing this equality here on a column by column basis tells me that every column of R is equal to P times the corresponding column of A. So if we have a relation in the columns of R, like this R5 equals minus R1 plus R4, well, that's the same as writing that PA5 is equal to minus PA1 plus PA4. And I can manipulate this a little bit. I get PA5 equals to P times minus A1 plus A4. Now multiply both sides by P inverse on the left. That will cancel the P's. So we get, well, P inverse PA5 equals P inverse P minus A1 plus A4. Now P inverse P become identity matrices, so I get my relation A5 equals minus A1 plus A4. And you see those two relations are the same, except one is written with the columns of R and one is written with the columns of A. This consequence is so important that it deserves a theorem to just pack it all together. What we just saw is that if I give you any matrix A, then its pivot columns are linearly independent because the corresponding columns in the row-reduced echelon form are, and its non-pivot columns are linear combinations of the pivot columns whose coefficients match the corresponding coefficients in the reduced row echelon form. The theorem is a mouthful, but it's exactly what we've been doing. We can do it again in this example here. In this example, we're assuming that we don't know what A is, but we know it's reduced echelon form. So without even knowing what A is, we know that the set, well, let's analyze this reduced echelon form. The pivot columns are the first and the third in here. So we know that the set A1, A3 is linearly independent. And we know that there are relations between the columns of A. A2 is equal to twice A1, and A4 is equal to A1 plus twice A3. It's a crucial property. Let's move on to the third one, which is a slide. It's really a consequence of the second property. So our third consequence is that the reduced row echelon form of every matrix is unique. The reason why that's true is that it's uniquely determined by the matrix A. If a set of matrices of columns of A are linearly independent, then the corresponding vectors, the corresponding columns in the matrix R will be standard vectors. So they will be completely determined by their position because there's nothing to choose about a standard vector. And if AI is a certain linear combination of other columns in A, then Ri is determined by the same coefficient with a linear combination of other columns, R1 to Ri minus 1. In other words, the columns of A, being them linearly independent or dependent, determine exactly the columns of the reduced row echelon form, which is therefore unique.